It is a land of superlatives, the coldest, driest and highest continent on Earth. But perhaps the most astonishing fact about Antarctica is not what we see on its surface, but what lies hidden beneath its immense frozen shield. Deep below kilometres of solid ice, there exists a world that has been cut off from our own for millions of years. It is a realm containing vast mountain ranges taller than the Alps, hundreds of interconnected liquid lakes and sprawling river systems, all moving and flowing in total darkness. This is not a dead continent, but a dynamic, secret world, one that holds clues to our planet's past and critical warnings for its future. The sheer scale of this hidden geography is difficult to comprehend. A continent within a continent. Imagine standing on a seemingly endless plain of white, where the horizon dissolves into the sky. Beneath your feet, more than 4 kilometres down, lies a landscape as complex and varied as any on the surface of our planet. This is the great paradox of Antarctica. Its surface suggests a simple monolithic emptiness, a brutalist architecture of ice and wind. Yet the truth is far more intricate. The ice sheet, which appears so static, is in fact a colossal, slow-moving glacier, grinding and shaping the continent below. It is a world preserved, a snapshot of a time before ice claimed the land. And it is only now, with our modern ingenuity, that we are beginning to pull back the curtain on its profound mysteries. This hidden world is not merely a geological curiosity. It is a vital component of our global system. The processes occurring beneath the ice, the flow of water, the grinding of rock, the potential existence of unique life, have far-reaching consequences that touch every corner of the Earth. The continent acts as our planet's great refrigerator, regulating temperatures and driving ocean currents that distribute heat around the globe. Understanding what happens in this concealed realm is therefore not just an academic pursuit. It is essential for understanding the stability of our own world and the climate that allows us to flourish. The secrets of Antarctica are, in many ways, our own. For generations, we looked at Antarctica as a final frontier, a blank space on the map marked only by the courage of early explorers. But the true exploration has only just begun. We are moving beyond the challenge of surviving its surface to the far greater challenge of perceiving its depths. With every new piece of data, our picture of this buried continent becomes richer and more astonishing. We are discovering that this place we thought was desolate is, in fact, brimming with complexity and a strange, dark vitality. The story of Antarctica is the story of discovery itself, a reminder that our planet still holds wonders beyond our wildest imaginings, waiting patiently to be found. To truly appreciate the wonder of Antarctica's hidden world, one must first grasp the sheer scale of the ice that conceals it. The Antarctic ice sheet covers an area of almost 14 million square kilometres, larger than Europe. On average, this ice is over 2 kilometres thick, but in some places it plunges to depths of nearly 5 kilometres. This is not just a layer of frozen water. It is a geological force of unimaginable power. It has depressed the very bedrock of the continent, pushing some areas far below sea level. This immense weight has also insulated the world below, preserving it from the dramatic climate shifts that have reshaped the rest of our planet's surface over millions of years. Beneath this colossal blanket of ice lies a topography of breathtaking diversity. There are vast basins, deep trenches and rolling plains, all sculpted by ancient rivers and glaciers from a time before the Great Freezing. This is a ghost landscape, a world that has not seen sunlight for at least 15 million years. When we use our technology to peer through the ice, we are essentially looking back in time. We see the remnants of a continent that was once connected to Australia and South America, a land that may have been covered in forests and teeming with life. The ice sheet acts as the ultimate museum curator, preserving this ancient world in a state of suspended animation, safe from erosion and change. The pressure exerted by the ice is so immense that it behaves in ways that defy our everyday intuition. At the very bottom of the ice sheet, where it meets the bedrock, the colossal weight generates geothermal heat from the Earth's core and friction, causing the ice to melt. This creates a thin, crucial layer of water that lubricates the base of the ice sheet, allowing it to slide slowly but inexorably toward the sea. This basal melting is the lifeblood of the subglacial world, feeding the hidden lakes and rivers that crisscross the continent in a complex plumbing system. It is a world born of pressure, darkness, and the strange physics of ice. Therefore, the Antarctic ice sheet is not a static feature. It is a dynamic, living entity, constantly in motion. It flows, it grinds, it melts, and it refreezes. Its movements are dictated by the hidden landscape beneath it, just as a river's flow is guided by its channel. The valleys and mountains of the buried continent steer the ice into fast-flowing ice streams, which act as arteries, transporting ice from the interior to the coast. Understanding this intricate dance between the ice above and the land below is the key to predicting how Antarctica will respond to a warming world, and what secrets it may yet reveal as it changes. Perhaps the most startling feature of this hidden continent is a mountain range as grand as the European Alps, yet entirely buried beneath kilometers of ice. These are the Gamburtsev subglacial mountains, discovered by a Soviet Antarctic expedition in 1958. For decades, their true scale and nature remained a mystery. They lie near the centre of East Antarctica, a region once thought to be a flat, featureless plateau. The discovery was akin to finding the Himalayas hidden under the Sahara Desert. These are not mere hills, but jagged peaks rising to 3,000 metres and stretching for over 1,200 kilometres, all entombed in an icy mausoleum. The very existence of the Gamburtsevs posed a profound geological puzzle. Mountain ranges are typically formed by the collision of tectonic plates or by volcanic activity. Yet these mountains are in the middle of an ancient, stable continental craton. Furthermore, high, jagged peaks are usually geologically young, as erosion wears them down over millions of years. But the Gamburtsevs are ancient, believed to have first risen over 1 billion years ago, and then experienced a final uplift around 250 million years ago. The reason they remain so sharp and majestic is the ice itself. The ice sheet grew around them, preserving their peaks from the erosive forces of wind and rain that would have long since ground them into dust. Scientists have used ice-penetrating radar and other geophysical methods to map this invisible mountain range in stunning detail. The images they have created reveal a landscape of sharp ridges, deep valleys, and dramatic escarpments. It is a world that looks as if it were flash-frozen yesterday, not millions of years ago. In the valleys of the Gamburtsevs, scientists have found evidence of pre-glacial river networks, the very places where the first Antarctic glaciers began to form. It is here, in the cradle of these mountains, that the great ice sheet was born, slowly growing and spreading outwards until it consumed an entire continent. The Gamburtsev Mountains are more than just a geological marvel. They are the heart of the East Antarctic ice sheet, the largest and most stable mass of ice on the planet. The high peaks of the range act as a point of nucleation, where snow accumulates and compacts into the dense ice that feeds the surrounding sheet. Understanding the interaction between these buried mountains and the ice above them is critical. The rugged topography influences how the ice flows, creating areas of both stability and faster movement. These ghost mountains, unseen by any human eye, are a cornerstone of the Antarctic system and, by extension, the global climate. One of the most profound discoveries in this subterranean world is that it is not entirely frozen. Beneath the ice, Antarctica harbours a vast network of more than 400 subglacial lakes. These are not small ponds, but enormous bodies of liquid water, some as large as the Great Lakes of North America. The most famous of these is Lake Vostok, located in the heart of East Antarctica. It is one of the largest lakes on Earth by volume, buried under nearly 4 kilometers of ice. Its waters have been isolated from the surface world for an estimated 15 million years, creating a pristine environment that is utterly unique on our planet. How can liquid water exist in the coldest place on Earth? The answer lies in two simple principles of physics. Firstly, the immense weight of the overlying ice sheet creates incredible pressure, which lowers the freezing point of water. Just as salt on a road helps melt ice, pressure at the base of the ice sheet keeps the water liquid at temperatures that would normally be well below freezing. Secondly, geothermal heat flowing from the Earth's core gently warms the bedrock, providing just enough energy to maintain these vast liquid reservoirs. This delicate balance of pressure and warmth creates the conditions for a hidden hydrosphere. These lakes are not static, isolated pools. Evidence suggests that many of them are interconnected by a system of subglacial rivers and channels, forming a continent-spanning plumbing system. Water may flow from one lake to another, a process that can take thousands of years. This slow-motion circulation has profound implications. It means that heat, nutrients, and potentially microbial life could be transported across vast distances beneath the ice. The discovery of this active water system transformed our understanding of Antarctica from a static block of ice to a dynamic and complex hydrological system, one that is constantly, if slowly, changing and evolving in the dark. The existence of these ancient isolated lakes presents a tantalizing possibility. The existence of life. For millions of years, these bodies of water have been completely sealed off from the atmosphere and the sun. Any life that might exist there would have had to evolve in total darkness, under extreme pressure, and with very few nutrients. It would be a form of life entirely alien to our sun-drenched surface world, surviving perhaps on minerals scraped from the rocks below. Exploring these lakes is one of the great quests of modern science, as it offers a glimpse into how life might survive in other extreme environments, such as on the icy moons of Jupiter and Saturn. Just as continents on the surface have rivers that drain their landscapes, so too does the world beneath the ice. Scientists have mapped enormous channels and river systems that transport water from the interior of the continent towards the coast. These are not gentle streams. Some of these subglacial river systems are longer and carry more water than the River Thames. They are carved into the bedrock by the constant slow-moving flow of meltwater generated at the base of the ice sheet. This water, guided by the underlying topography of buried valleys and plains, forms vast unseen drainage basins that are fundamental to the continent's behaviour. The flow of these hidden rivers is a critical factor in the movement of the ice above. The water acts as a lubricant, reducing friction between the ice and the bedrock. Where these rivers are concentrated, they can create conditions for much faster ice flow. This leads to the formation of ice streams, which are veritable rivers of ice that can move at speeds of up to 1 kilometre per year, funneling vast quantities of ice from the high interior plateau down to the Southern Ocean. The pathways of these subglacial rivers therefore directly influence where and how quickly Antarctica loses its ice, a process with direct consequences for global sea levels. Mapping these river systems is a monumental challenge. Scientists use airborne radar that can penetrate the ice sheet, sending radio waves down to the bedrock and back. By analysing the echoes, they can distinguish between solid rock, liquid water, and saturated sediments. The data they collect allows them to build up a detailed picture of this dark, watery network. What they have found is a system of extraordinary scale and complexity, with tributaries, main channels, and even subglacial deltas where the rivers meet the ocean beneath the floating ice shelves. It is a complete, functioning river system, operating entirely without sunlight. The discovery of these rivers also changes our perspective on the potential for life. A flowing river system, even one moving in slow motion, can transport minerals and chemical nutrients from the rock over which it passes. This could provide a vital source of energy for microbial ecosystems that may be clinging to life in the subglacial lakes. The rivers act as a potential distribution network, connecting otherwise isolated habitats and allowing for the exchange of genetic material. The dark rivers of Antarctica may not just be shaping the ice. They may be sustaining a hidden biosphere, a web of life that has been waiting for millions of years for us to find it. Antarctica is much more than a remote frozen landmass. It is a principal driver of the Earth's entire climate system. The continent acts as a giant heat sink, its vast white ice sheet reflecting up to 80% of incoming solar radiation back into space. This phenomenon, known as the albedo effect, is crucial for keeping our planet cool. Without the reflective power of Antarctica's ice, the Earth would absorb significantly more solar energy, leading to a much warmer global climate. The continent's role as the world's refrigerator is fundamental to maintaining the relatively stable temperatures that have allowed human civilization to thrive for the past 10,000 years. The influence of Antarctica extends deep into the world's oceans. As seawater freezes around the continent's coast, it expels salt, creating incredibly cold, dense brine. This super-salty, frigid water sinks to the very bottom of the ocean floor, a process known as Antarctic bottom water formation. This sinking water then creeps northwards along the seabed, forming a deep, slow-moving current that drives a global circulation system, often called the ocean conveyor belt. This circulation is vital. It transports oxygen to the deep ocean, allowing marine life to exist at all depths, and it helps to distribute heat from the tropics towards the poles, moderating climates worldwide. The health of this climate engine is directly tied to the stability of the ice. The melting of ice shelves, the floating extensions of the main ice sheet, can disrupt this delicate process. As fresh water from melting glaciers pours into the Southern Ocean, it dilutes the salty surface water, making it less dense. This fresher, lighter water does not sink as readily, which can slow down the formation of Antarctic bottom water. A slowdown in this great ocean conveyor belt would have profound and unpredictable consequences, potentially altering weather patterns, disrupting marine ecosystems, and accelerating warming in certain parts of the world. The pulse of Antarctica's freezing and melting is felt in oceans thousands of miles away. Furthermore, the Antarctic ice sheet itself is a colossal repository of our planet's climate history. The ice has formed over hundreds of thousands of years from accumulated snowfall. Each layer of snow traps tiny bubbles of the ancient atmosphere. By drilling deep into the ice and extracting ice cores, scientists can analyze these bubbles to measure past concentrations of greenhouse gases like carbon dioxide and methane. This frozen archive gives us an unparalleled record of our planet's climate, showing us how closely temperature has been linked to greenhouse gases throughout Earth's recent history. The ice not only regulates our present climate, but also holds the key to understanding its past and predicting its future. For decades, the world beneath Antarctica's ice was assumed to be sterile, a place too dark, cold, and nutrient-poor to support any form of life. The discovery of liquid water in subglacial lakes and rivers changed that perception entirely. It opened up the tantalizing possibility that life could exist in these isolated environments, evolving in complete isolation for millions of years. This would be life as we have never seen it before, adapted to survive under kilometers of ice, in total darkness, under crushing pressure, and on a diet of whatever meagre chemical energy it could extract from rock and water. The first direct evidence of life came from samples drilled from subglacial environments. In 2013, scientists successfully drilled through 800 meters of ice into Lake Whillans, a relatively shallow and active subglacial lake. The water they brought to the surface, which had not been in contact with the atmosphere for millennia, was teeming with microbial life. They found a diverse community of bacteria and archaea, numbering around 130,000 cells per milliliter of water, a density similar to that found in the deep ocean. These organisms were not just dormant, they were active, metabolizing and forming a functioning ecosystem in the dark. These microbes are a testament to the tenacity of life. They are chemosynthetic, meaning they derive their energy not from sunlight like plants, but from chemical reactions. They eat minerals from the fine sediment ground up by the glacier above, such as ammonium and methane, which are trapped within the ice and released as it melts. They are the primary producers in this dark world, forming the base of a food web that operates entirely independently of the sun. The discovery of this ecosystem proved that life could thrive in one of the most extreme and inaccessible environments on Earth, expanding our definition of where life is possible. The implications of this discovery are truly profound. It suggests that a hidden biosphere may exist across much of the continent, sustained by the network of subglacial lakes and rivers. Furthermore, it provides a powerful model for the search for extraterrestrial life. Moons in our outer solar system, such as Jupiter's Europa and Saturn's Enceladus, are believed to have vast liquid water oceans hidden beneath their icy shells. The conditions in these alien oceans, dark, cold and under pressure, may be remarkably similar to those in Antarctica's subglacial lakes. The life found beneath Antarctica's ice gives us hope that we might one day find that we are not alone in the universe. Exploring a world buried beneath kilometers of solid ice is one of the greatest technological challenges in modern science. We cannot simply go there. Instead, scientists must act as remote detectives, using a remarkable array of sophisticated tools to piece together a picture of this invisible landscape. The primary method for mapping the world beneath the ice is ice-penetrating radar. This technique involves flying an aeroplane equipped with a special radar system back and forth across the ice sheet in a grid pattern. The radar sends pulses of radio waves downwards, which travel through the ice and reflect off the bedrock below. The time it takes for these radio waves to travel down and back reveals the thickness of the ice. More importantly, the strength and character of the returning signal can tell scientists what the radar has encountered. Solid, dry bedrock produces a strong, clear echo. Liquid water, however, absorbs the radar signal, creating a telltale flat and mirror-like reflection. It was this distinctive signature that first led scientists to identify the great subglacial lakes like Vostok. By painstakingly assembling thousands of these radar lines, researchers can create stunningly detailed three-dimensional maps of the mountains, valleys and lakes hidden from view. To complement radar data, scientists also use other geophysical methods. For instance, they measure tiny variations in the Earth's gravitational field. A massive mountain range hidden under the ice will exert a slightly stronger gravitational pull than a deep basin, and these minute differences can be detected by sensitive instruments. Similarly, magnetometers can be used to map the magnetic properties of the rock beneath the ice, helping geologists understand the underlying rock types and tectonic structures. By combining radar, gravity, and magnetic data, Scientists can build a comprehensive and multi-layered view of the subglacial continent. The ultimate goal, however, is to obtain direct samples from this hidden world. This requires the monumental feat of clean, hot water drilling. To avoid contaminating these pristine environments, which have been isolated for millions of years, scientists have developed highly specialized drills. These drills use a jet of heated filtered water to melt a hole through the ice sheet. The entire system must be sterilized to a medical-grade standard to ensure that no surface microbes are introduced into the subglacial environment. It is a slow, painstaking process, but it is the only way to retrieve water and sediment samples that can tell us for certain what life exists in the darkness below. The great Antarctic ice sheet, which has been relatively stable for millions of years, is beginning to change. The warming of our planet's atmosphere and oceans is having a profound and accelerating impact on this frozen continent. The consequences of this melting are not confined to Antarctica. They are global. The most direct and widely understood impact is sea level rise. Antarctica holds about 90% of the world's ice, which is equivalent to around 60 meters of potential sea level rise. While the entire ice sheet is not going to melt overnight, even a small percentage of loss would have catastrophic consequences for coastal communities around the world. The melting is not happening uniformly. The massive East Antarctic ice sheet remains relatively stable for now, protected by its sheer size and extreme cold. The real concern is the West Antarctic ice sheet. Much of its base rests on bedrock that lies far below sea level. This makes it inherently unstable. As warming ocean water nibbles away at the base of the floating ice shelves that buttress the main ice sheet, these natural dams are weakening and thinning. If they were to collapse, it could trigger a rapid and potentially unstoppable retreat of the glaciers behind them, a process known as marine ice sheet instability, which would release vast amounts of ice into the ocean. However, the melting of the ice also has another, more ironic consequence. It is a catalyst for discovery. As the ice thins and retreats, it is beginning to unveil parts of the hidden world that have been concealed for millennia. Ancient landscapes, geological formations, and perhaps even preserved ecosystems could be exposed. While this is an exciting prospect for scientists, it is a bittersweet one. Each new piece of land revealed is a stark reminder of the ice that has been lost. We are gaining knowledge of a hidden world at the direct expense of the stability of our global climate system, a trade-off that carries a very heavy price. The changes in Antarctica will also reshape life on and around the continent. Species that depend on sea ice, such as Adelie penguins and krill, are already facing challenges as their habitat shrinks and changes. The influx of fresh water into the Southern Ocean alters its chemistry and circulation, with cascading effects on the entire marine food web, from the smallest plankton to the great whales. The unravelling of Antarctica's ice is not just a physical process, it is a biological one, threatening to disrupt one of the world's last great wildernesses and sending shockwaves through the global ecosystem. The fate of this remote continent is inextricably linked to our own. The secret world beneath Antarctica is a place of profound wonder, a testament to the enduring power and mystery of our planet. It holds the keys to understanding our climate's past, the potential for discovering unique forms of life, and stark warnings about our planet's future. For all its remoteness, Antarctica is not a separate world. It is an integral part of the Earth system, a continent whose frozen heartbeats regulate the oceans and atmosphere that sustain us all. What happens in Antarctica does not stay in Antarctica. It is felt on every coastline, in every weather pattern, and by every living creature on Earth. The future of this extraordinary continent now rests in our hands. The discoveries we are making about its hidden lakes, mountains and rivers are occurring at the very moment that its future is most threatened. The science is clear. The continued warming of our planet, driven by human activity, is pushing the Antarctic system towards a tipping point. Protecting this continent is not merely an act of preserving a beautiful and remote wilderness, it is an act of self-preservation. The stability of the ice sheet is fundamental to the stability of our own societies, and we have a collective responsibility to ensure its protection for generations to come. This responsibility is enshrined in the Antarctic Treaty, a remarkable achievement of international cooperation that sets the continent aside for peace and science. But treaties alone are not enough to protect it from the pervasive influence of a warming climate. The most meaningful action we can take to protect Antarctica is to reduce our greenhouse gas emissions and transition to a sustainable way of living. We must listen to the messages that the ice is sending us, messages recorded in ancient air bubbles and written in the accelerating flow of its glaciers. The fate of Antarctica is a referendum on our ability to act collectively in the face of a global challenge. There is still reason for hope. Our capacity for discovery, which has allowed us to peer beneath the ice, is matched by our capacity for innovation and cooperation. By understanding the intricate workings of this hidden world, we are better equipped to protect it. The story of Antarctica is ultimately a story of connection, the connection between ice and rock, between a hidden continent and the global climate, and between human actions and planetary consequences. Let us choose a future where this continent of secrets remains a source of wonder and stability, a symbol not of what we have lost, but of what we have had the wisdom to preserve.